hardcore organic chemistry now. All right, everybody. So this is chapter 4. It deals with alkanes and cycloalkanes. And I was just telling the class before we came online and before I started recording that sometimes we refer to alkanes. There's an old historical term that we use, which is paraffins. Paraffin. So if you ever hear of a paraffin, they're referring to an alkane. Anyhow, we don't really use that term anymore, so I'll remove that. Another thing I want you to think of is that the only atoms we're going to see in this chapter are carbon and hydrogen. And if we have a carbon-carbon bond, the difference in electronegativity is going to be 0. And if we have a carbon-hydrogen bond, the difference in electronegativity there is going to be equal to 0.4, which is less than 0.5. And therefore, everything that we see in this chapter is going to be nonpolar. So everything is going to be nonpolar. We don't have to worry about dipoles and any of that kind of stuff. All right, so another thing is that this chapter will require some serious memorization. You have to memorize the names of the first 10 straight chain alkanes, and you also have to memorize the names of the first, or not the first, but you have to memorize 8 common alkyl groups, and I'll go over those with you in a little bit. So let's start off by talking about what an alkane is exactly. So you heard me talk about hydrocarbons before, and I think I've already mentioned them today. A hydrocarbon is simply something that is made of only hydrogen and carbon. And as I just explained, if you have any kind of hydrocarbon, and there's 4 of them shown here, they're all going to be nonpolar compounds because there's no polar bonds in a hydrocarbon. It's impossible. Now, in this class, in this chapter rather, we're going to focus on alkanes. And ethane would be an alkane. And we say that an alkane is saturated because it has no double bonds in it, okay? So no double bonds, or no pi bonds. Maybe I should put that in here. No pi bonds. But that's technically, anyhow, there's some technicality to that. You could just say all single bonds or no pi bonds. But you see that everything else is unsaturated, and all of those have pi bonds in them. For example, an alkene. Ethylene is an alkene. And you can see we have a pi bond in there. Acetylene is an alkyne, and we see that there's 2 pi bonds in it. And then benzene, we call that an aromatic. And even though it's a hydrocarbon, it's not an alkane, it's an aromatic, and it has 3 pi bonds in it. So unsaturated versus saturated. Another way to think of saturated is that in a saturated hydrocarbon, you have, we'll put it here, maximum number of hydrogens per carbon atom. Okay, for every carbon atom that's in the molecule, you have a maximum amount of hydrogens. You cannot put any more than is in a saturated hydrocarbon. There we go. So again, we're going to focus on alkanes in this chapter, and ethane would fall under the umbrella of an alkane. We're also going to talk about cycloalkanes, but I'll get into that in a second. So if you're wondering about naming alkanes, well, I'm going to give you a systematic way to name alkanes in just a second. But just so you're aware, there are all kinds of names of organic compounds that are just historical, really. It's just somebody gave a name and that's it, and it's kind of stuck. You know, for example, if you look at any kind of marketed drug, so if you think about a drug, and I'm talking about a prescription drug, okay, it's going to have some kind of IUPAC name, which is a systematic way of naming it, but it's also going to have a generic name, okay? If you think about, you know, generics, they, you know, sell drugs, so they always come up with a generic name. And then it's also going to have a trade name. So we use different ways to describe drugs. But that's kind of another subject. If you look at something like formic acid, if you're wondering where does the name formic acid come from, it's formic acid is actually used as a defensive spray by some kind of ants. Don't ask me what kind because I don't know. But you see the Latin word for ant is formica or formica. So that's where formic acid comes from. Urea, that one's probably a little more obvious. It comes from urine. Morphine, if you've ever had the pleasure of being administered morphine, even if you were in a lot of pain, it can make you feel pretty good pretty quick. And morphine is named after Morpheus, who's the god of dreams. So that one's kind of funny. And barbituric acid is another great one. It was named by Adolf von Baer, and he named it after, it says here, in honor of a woman named Barbara. What I always heard was that he was infatuated with this woman named Barbara, and he just decided to name barbituric acid after it. So if you've ever heard of the illegal drugs that, you know, people take sometimes called barbiturates. They would be derivatives of barbituric acid. Anyway, kind of a funny thing there. Now, we're not going to name compounds like that. You don't have to memorize common names like caffeine and things like that. What you need to do is you need to be able to apply the IUPAC rules and give a systematic name to an alkane or a cycloalkane in this chapter. Okay, so how do we do that? Well, let's go through the rules. There's a few of them. They're kind of interesting. The first one is you identify the parent chain. Okay, and if you're like, well, what's the parent chain? The parent chain is the longest consecutive chain of carbon atoms in the molecule. So if you look at this molecule here, walking down the street, you see this molecule, and you say, I want to give this molecule a name. I'm going to call it Gary. No, you can't do that. What you've got to do is you've got to find the longest chain. And the way you find the longest chain is by T&E, trial and error. Okay, so what you do is you say, well, maybe 1, 2, 3, 4, 5, 6. No, that's not that long. Hold on. What if we do something like 1, 2, 3, 4, 5, 6, 7, 8? No, that's not it. And then you see that the book has identified that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That is, in fact, the longest carbon chain. And if you're wondering, is that how I'm going to find it? Is just keep looking until I find it? Oh, yeah, that's how you're going to find it too, okay? So, students will sometimes think, well, shouldn't it just be laid out for me, in a straight, line like this? Sometimes, yeah, but sometimes no. It might twist, it might turn, it might bend. So you just have to look until you find it. Okay, so first thing is find the longest carbon chain. And then you have to give a name to that parent. So how do you name the parent? Well, you're going to apply one of these names over here. So you need to memorize the first 10 straight chain hydrocarbons. So I'm going to put over here, memorize, okay? That if you have one carbon, we call that methane, so CH4. All right, I'll just pencil the first couple in here. If you have CH4, that's methane. If you have CH3, that's ethane, so 2 carbons. If you have 3 carbons, CH3, CH2, CH2, CH3. What am I doing here? That's not 3, that's 4. Come on, Mr. Dion. There we go, that's propane. And then you'd go to butane, which is 1, 2, 3, 4. Pentane is 1, 2, 3, 4, 5. I want to keep adding extra carbons. 1, 2, 3, 4, 5. Hexane has 6 carbons. 1, 2, 3, 4, 5, 6. Heptane has 7. 1, 2, 3, 4, 5, 6, 7. Octane has 8. 1, 2, 3, 4, 5, 6, 7, 8. Nonane and decane, so on and so forth. You do not need to memorize undecane, dodecane, tridecane, tetradecane, pentadecane, etc., icosane, and all that kind of stuff. So you just need to memorize the first 10 straight chain alkanes. And you know what's funny is that when we have them in a line like this, so linear chains, sometimes we call those N-alkanes. So N-alkanes, and the N actually stands for normal alkanes, and that means it's going to have a straight chain, okay? So N stands for, it's just going to have a straight chain, all right? So methane, ethane, propane, butane, pentane, right? You think of a pentagon is 5 sides, a hexagon has 6, so that's easy to remember. Hept, I don't know about that one. You go to oct, right? The octagon, then nonane, kind of sounds like the number 9, right? Nonane, and then decane, well, you know what a decade is. So really, the only ones that are kind of tough to remember are methane, ethane, propane, and butane, I guess. All right, so you need to know the first 10. So if we go back to this compound here, the parent in here, since we have 9 carbons on the parent, this compound is some kind of nonane, okay? So this is a nonane, and if you're sitting there going, well, what do you mean by a nonane? Well, you have something here, something here, something here, and something here that you haven't identified yet. So we would say the parent, the longest chain, is the nonane, and that parent is going to come last in the name. Now, if you're wondering, you said this chapter was about alkanes and cycloalkanes. Well, when did they show up? Here you go. So if you have a parent chain, and which is cyclic, so where you tie the 2 ends of a chain of carbons together, then we prefix it with cyclo. Since we have 3 carbons here, we would call this cyclopropane, right? 4 carbons would be cyclobutane, cyclopentane, and then of course you could draw cyclohexane. So this would be cyclohexane. And one of my students threw me a meme a couple of years ago, and it says, things I learned in organic chemistry, how to draw hexagons. And there's a good reason why we spend so much time talking about cyclohexane. I'm not going to get into that right now. If you want to draw a cycloheptane, you have to draw a 7-sided ring. I'm not that great at it. So cycloheptane, right? And then cyclooctane, that's an octagon. So that's going to look like this, kind of like a stop sign. So this would be cyclooctane. Cyclononane and cyclodecane, you're on your own if you want to draw those. All right. So if it's cyclic, we prefix it with cyclo. Everybody with me so far? Thumbs up if you're with me so far. Follow me along with the alkanes and then the cycloalkanes. Cool. Good. All right. Well, let's move on from there. And if you're wondering, well, what about those little things that were dangling off the side that you put in the blue circles? Here, 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 and here. We call those alkyl groups. And now I'm going to introduce to you the alkyl groups that you need to have memorized. And so if you have a straight chain alkyl group, meaning it's just one carbon after another and there's no branching, the ones that we're going to use in this class, mostly, I would say 95% of the time, would be the first four. So the first four. So let's say if you have a CH3 group, that's a methyl. And then if you have 2 carbons, it's an ethyl, 3, it's a propyl, 4, it's a butyl. So a methyl group is nothing more than a CH3 attached to something. An ethyl group is CH3, CH2 attached to something. A propyl, CH3, CH2, CH2 attached to something. And then a butyl is CH3, CH2, CH2, CH2 attached to something. Pentyl is 5 carbons, etc., etc., etc. But these first 4 we're going to use quite a bit. So if we were to identify the first one here, okay, could anybody identify this one here? Would this be a methyl, ethyl, propyl, or butyl? The one I have in the red circle. Yeah, thanks, Sean. Absolutely, this is an ethyl group. Yeah, can't argue with that. Thanks, Sarah. Thanks, Eric. What about this one here? If I have 3 carbons like this, could anybody identify this guy? Yes, this is a propyl group. Propyl, right? We have CH2, CH2, CH3, so that's a propyl group. And what about the very last one here? If you just have a CH3, what do we call this guy? Yeah, thanks, Sarah. This is a methyl group. All right, there you go. If we go, come on, let's do it. We got time. Plus, it's fun, right? If you look at this one, this is a methyl group. Everything else is an ethyl. This is an ethyl. This is an ethyl. And this one here is also an ethyl. All right. Okay, so we've covered those. Now, it says here, a ring, what's interesting about a ring is the ring can be the parent. If it's the longest carbon chain, then it's the parent. However, a ring can also be a substituent if it's not the longest carbon chain, okay? So when you're numbering a chain, right, you can't go 1, 2, 3, 4, 5, 6, 7. You can't do that. You can't go over a carbon a second time, okay? Students will sometimes want to do that. So we see that the longest carbon chain in this molecule on the left has a total of 6 carbons in the ring, and then you have a propyl group attached to it, right? This would be a propyl here. So we'd call this propyl cyclohexane, right? The parent comes last. But on the next one, you see that you have a cyclopropyl. That's only got 3 carbons, and the parent has a total of 1, 2, 3, 4 carbons. So it's some kind of butane. So we would call this 1-cyclopropyl butane because the cyclopropyl is attached to the first carbon. If you're wondering about the numbering thing and the order, don't worry, we're going to get to that in just a second. Okay, now what if you have a substituent that's really complex? I need to refer to my notes for this because there's only one example about this, I think, in the entire textbook. I think it's question number 4.13 is the only time they give you a substituent with a complex branch, but it is part of the content of the course, so I'm obliged to teach it to you. And I think it's also mentioned in Skill Builder. Skill Builder 4.3. You have to fact check me on that, but I think it is. Okay, so for a complex branch, if it doesn't fall under the umbrella of something that I taught you, well, in that case, you've got to give it a systematic name. And the way you do that is you number the longest chain within the substituent. So the longest chain within the substituent has a total of 4 carbons. And so it would be a butyl group. And then we number and name any substituent. So we have a 2-methyl on the butyl group. So right, this is a methyl. So we'd call it 2-methyl-butyl. And then you put the whole thing inside brackets. I'll be honest, this whole complex substituents or complex branches or complex substituents, it might be worth the value of one multiple choice question on a quiz, okay? That's about it. Because what we're going to use the majority of the time are the common names for alkyl groups. And let me repeat, like I told you before class started, there's 8 of them you need to know. They are methyl, ethyl, propyl, isopropyl. Okay, so a methyl only has 1 carbon in it, and ethyl has, so this is 1 carbon, and ethyl has 2. Propyl and isopropyl both have 3 carbons. And then when it comes to 4 carbons, there's 4 different groups. You have to know butyl, isobutyl, sec with a hyphen, butyl, and tert with a hyphen, butyl. Okay, you need to know all of those, and they all have 4 carbons. So that's a total of 8 different alkyl groups that you need to have memorized. Okay, so let's go over them. We've already covered the methyl and the ethyl. We've also covered the propyl, right? The propyl, as I told you before, was CH2, CH2, CH3, right? There's no arguing the propyl group. So the thing is that the formula of this group here, maybe I'll just circle what's in blue here. The formula of this is C3H123456 C3H7. So it turns out there's a second way that you can organize C3H7. And that is, as we have shown here, check it out. We have CH, so that's a methine, CH3, and CH3. If you tally that up, that's C3H7. So it's an isomer of the propyl, and we call this an isopropyl. You could give it a complex branch name, 1-methyl-ethyl, but we almost never do that. Okay, maybe a question in the homework or something like that, but very rarely do we do that. Another thing is that you probably noticed, well, there's isopropyl and isobutyl. What you'll see is that they both end with 2 methyl groups, kind of coming off the end like this. The isobutyl does that too. Okay, so far we've covered methyl, ethyl, propyl, isopropyl. Give me a thumbs up if you're with me on that, or stop me if you have a question. Does anybody have a question about methyl, ethyl, propyl, and isopropyl? No? All right, then we'll move. And again, never be shy to ask me a question. I'm always happy to answer any question you have about this kind of stuff because it's challenging. Okay, so when we have a butyl group, there's going to be 4 possibilities. Why? We've got more atoms, so there's more ways to arrange them, right? If you look at the formula of a butyl, which is CH2, 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 CH3, like that, the formula is C4H12345678 C4H9. Well, it turns out that there are 4 different ways to organize C4H9. All of these are C4H9 as well. Okay? Only thing I can tell you, man, is you've got to memorize them. So we've got sec-butyl. Okay, so with a sec-butyl, we have a methine, which is a CH, and a methyl attached to it. Then we have a methylene, a CH2, and a methyl. So that's sec-butyl. And the isobutyl, remember, ends up with 2 methyl groups on the end, like this. Then you have a methine and a methylene here. And for the tert-butyl, you have a carbon that has no hydrogens attached to it. And then you have 1, 2, 3 hydrogens attached to it like that. So that is sec-butyl and tert-butyl. Notice that both of those have a hyphen. Okay. All right. And the isobutyl doesn't have a hyphen. So what's interesting about the ones that are hyphenated versus non-hyphenated, when you're alphabetizing butyl, you alphabetize according to the letter B. Sec-butyl, you alphabetize according to the letter B. Tert-butyl, you alphabetize according to the letter B. But isobutyl, since there's no hyphen in it, you alphabetize according to the letter I. And if you're like, why would they do that? I don't know. I didn't invent it. It's just the way it is. All right. So those are the 4 types of butyl groups outside of, you have butyl, isobutyl, sec-butyl, and tert-butyl. You have to have these all memorized. So if we go back to the list, now we've covered methyl, ethyl, propyl, isopropyl, butyl, isobutyl, secbutyl, interbutyl. You need to know them all. All right, there you go. So now if you're wondering, well, how do I put those number things in? You know, first of all, when you have a number, we call that a locant. So number is equal to, we call this a locant, okay? It says if one substituent is present on your parent chain, you number the chain in such a way that you give the substituent the lowest possible number. So we see here that the longest carbon chain is 7 carbons here. Okay, there's no arguing that. Same thing over here. Oops. All right, same thing over here. We have our 7 carbons here, 7 carbons here. But the way that it's numbered on the left, they started numbering it on the left-hand carbon, and that gives the methyl group, right? This is the methyl group. It gives it a locant of 2, or a number 2. So this would be a 2-methyl. So we would call this molecule 2-methyl, then the parent would be heptane, right? Because it's got 7 carbons in it. This is incorrect because it disobeys rule 1. Rule 1 says we number from the side or from the end that is going to give the first substituent the lowest possible number. Okay? So there we go. Now, if you have multiple substituents, and I kind of let this rule just slip out of my mouth by accident. If you have multiple substituents, here's the rule, and students seem to, not you guys wouldn't do this, but sometimes I'll have students who try to twist the rules and make them the way that they think they're logical, but here's the rule, is that you give the first substituent the lowest possible number. You don't have to add anything up and tally up stuff and add this and subtract that. There's none of that involved whatsoever. You just count the carbons. Wherever the first substituent shows up, whichever one has the lowest number, that's the answer. So if you look at the one on the bottom left, we go 1, 2, there's our first substituent, a 2-methyl. If you number from the right, you have 1, 2, 3, 3. So you'd say that's a 3,3-dimethyl, and I'll get into that in a second. But what's a lower number? 2 or 3? 2 is a lower number. Therefore, this is the correct way. Remember, it's got nothing to do with adding the numbers up. You don't need an abacus or a computer or Excel. You don't need any of that stuff. First substituent, lowest number, that's the answer. Okay, you start numbering from that position. All right. So if there's a tie, what do? You go for a tiebreaker. Okay. So you can see that in both of these, you have a methyl group on the second carbon, right? 2 and 6. And so you couldn't use that. But if you look at the one on the left, you go 1, 2, 3. There's your second substituent. Here you go 1, 2, 3, and there's no substituent. So the one on the left beats the one on the right. Give me a thumbs up if you're with me on that rule, or stop me if you have a question on that rule. That one's kind of an interesting rule. Another thing that can happen with tiebreakers sometimes is you can also break ties using alphabetical order, going from A to Z. If you have 2 substituents that are both on carbon 2, if you will, and one is a chloro and then one is a methyl, well, you would pick chloro because C comes before M. And if you're like, what's a chloro? A chloro would just be a chlorine, and I'll get into that in a second. So let's keep going on. Hey, what do you know? There's the rule right there. If there's no other tiebreaker, then we use alphabetical order. So here we have a chloro and a bromo. So chlorine is going to come, bromo is going to come first because B comes before C in the alphabet. Just so I can put this bug in your ear, if you have a fluorine substituent, we call that a fluoro. If you have a chlorine, as you just saw, we call that a chloro. If you have a bromine substituent, call that a bromo. And if you have an iodine substituent, we call that an iodo. Okay, fluoro, chloro, bromo, and iodo. Remember that fluorine is spelled F-L-U. Fluoro, fluorine. Okay, it's not fluorine or anything, or flour. That's what I get sometimes. All right, here we go. All the rules that we just looked at, they follow for a cycloalkane as well. So here we have some kind of cyclohexane, right? Remember when you have 6 carbons in a ring, no double bonds, that is cyclohexane, right? So if we look at the first one, you have 2 substituents, so you would call this carbon number 1, whereas this one, there's only 1. So you're going to start numbering it the way that it's numbered on the left. Okay. So if you're wondering, well, how do I put everything together into some kind of nomenclature sandwich? Here are the rules. You put the number and the name of each substituent before the parent in alphabetical order. So you'd put, let's imagine you had 2 bromo, 3 chloro, 5 ethyl, then 7 methyl, right? Something like that, right? So you can see that everything I put here, you put B, C, E, M, right? You put everything in alphabetical order. And then if you have 2 of the same substituent, you use prefixes. So if you have 2 of something, use di. If you have 3, you have tri. If you have 4, you would call it a tetra. If you have 5 of something, you would call that penta. 6 would be hexa, but I can't imagine when we have hexa anything. Maybe once in a while, I guess. 6 would be hexa. All right. Let's see here. Di and tri is ignored in alphabetization. So is iso. There's 2 other prefixes that are ignored when we're doing alphabetization. Iso plus cyclo is another one, and neo is another one. And if you're like, I've never even seen neo before, that's because I haven't taught it to you, but we might see that at one point in the course. All right. So here's the rules. Identify the parent chain. Identify names substituents. Is it a methyl, ethyl, sec-butyl, tert-butyl? Number the parent chain. Give a locant. So is it a 4-tert-butyl, etc.? List the numbered substituents before the name in alphabetical order. But here again, ignore prefixes, except, what were the 3 exceptions? Iso, cyclo, and neo. With those, we alphabetize according to I, C, or N. All right? And there you go. So with all that, we're going to come back to this compound. Let's go back to some of the ones that we didn't name. So if we, let's go all the way back here. Let's go back and name everything that we looked at, or at least most things that we looked at. So let's start with this one here. Okay, so if we use the rules for numbering, we're going to start numbering from here because we have 1, 2, 3 methyl. If you started numbering from here, you'd have 1, 2, 3, 4. So what's a lower number, 3 or 4? 3 is a lower number, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is, like I said, it's some kind of nonane. Okay, we have a 3 methyl and we have a 4, 5, 6 triethyl. So we ignore the prefix tri, but we use E, and that comes before M. So we have a 4, 5, 6 triethyl. So I'll put that in here, 4, 5, 6. All numbers are separated. If you have 2 numbers, they're separated by a comma. Numbers and letters are always separated by a hyphen. So 4, 5, 6 triethyl. And then we have a number and letter, so they're separated by a hyphen. 3 methyl. And then the parent is nonane. So there's the whole name of the compound, 4, 5, 6 triethyl 3 methyl nonane. Let's take a look. What was the next one we had? It was this guy here. Okay, which side am I going to start numbering from? The left-hand side or the right-hand side? I'm going to start numbering from the left, right? If I went from the right, I'd have 1, 2, 3, 4. Right here I have 1, 2, 3, 4. So I need a tiebreaker. 5, there's nothing there, and 5, there's something there. So I'm going to number it starting from the left. Somebody asked me, when do you put the alkyl group in parentheses? The only time you do that is when you're using a complex branch. That's when you put them in parentheses. So for this one, we have 5, 6, 7, 8, 9, 10. So this molecule is some kind of decane. And then let's see, we've got propyl, ethyl, and methyl. So ethyl is going to come first because of the letter E. Methyl is going to come second. And propyl is going to come third, right? Because we have E, M, and P. So we've got a 4-ethyl. So let me scribble that over here. We've got a 4-ethyl. Then we have a 7-methyl. And the last one is a 5-propyl. 5-propyl decane. There we go. So we named that one too. Anything else? Propyl cyclohexane, 1-cyclopropyl butane. That's good. With this one, so Sarah, to answer your question, we would put brackets around this one right here. The only thing is, this one's got such a long chain. I don't know if we covered a chain this long. So let's see. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Doesn't matter if you start numbering from the left or the right for this one. It doesn't change anything. And so what we're going to do is we'll just start numbering from, I don't know, let's start from the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is some kind of undecane. So this is an undecane. And then we have the complex branch here. So we have 2-methylbutyl. So we'd call this, what would it be? 6-2-methylbutyl undecane. So let me see here. It would be 6-2-methylbutyl hyphen undecane. Well, let's see if I can squeeze that all together somehow. So put it like that. There you go. So there's an example where you have to use the parentheses. It's when you have a complex branch. What else do we have here? We've named everything else, I think. Oh, we didn't. Yeah, we named this guy. We haven't named this one. Could anybody come up with a name for this compound? I'll give you a second to think about it. See if you can come up with a name for this guy here. Does anybody just think they might have a name? Yeah, I would agree with that. Somebody put 2,5,5 trimethyl heptane, and I would say, heck yeah, that's perfect. Yeah, nothing wrong with that. Everybody seemed to nail that one. Good. Good one. We'll put it up here, I guess, like that. Good. And this one here is in the same vein. There's a lot of compounds we didn't name here. This would be a 2,3,6 trimethylheptane. Trimethylheptane, like that. This one, it would be 1-bromo, 5-chloro. The parent has 5 carbons, so that's pentane. Good, so we got that one. This one here would be 1,1,3 trimethyl cyclohexane, because cyclohexane is our parent. Where do we get to the practice problems? With all that in mind, there we are. Okay, so you can see that we have a 1,1-dimethyl, and we have a 3-ethyl, and we have a 4-butyl. Could anybody tell me the parent of this one? What would be the parent for this guy? The parent has the longest chain, right? It has a total of 6 carbons. So it's a cyclohexane. Good, thanks, Sean. Yeah, cyclohexane. So we're going to put 4-tert-butyl, 4-ethyl, and then dimethyl. So this is going to be 4-tert-butyl, 3-ethyl, 1,1-dimethyl, because we ignore the prefix di. Dimethyl, or diethyl, no, dimethyl cyclohexane. There you go, 4-tert-butyl, 3-ethyl, 1,1-dimethyl cyclohexane. Wow, that's a long one. All right. Why couldn't you start from the top of the structure to give it 7 carbons? Well, I'm not sure what you mean by the top. Are you talking about this compound? Could you unmute your mic and explain that one?
Yeah, so for that structure, at the very like if you start from that middle methyl at the top.
This one?
Yeah, and then you go
here?
down with a bit more. Yes.
No, because you can't go outside of a ring, right? So you mean like 1, 2, 3, 4? No, because then you'd have to come around, and so a ring is an island unto its own. So you have to go 1, 2, right? We have to go 1, 2, 3, 4, 5, 6, like that. A ring is
so a ring
unto itself.
Be the parent.
Yeah, you can never go off a ring or on a ring.
Okay, thank you.
Yep, no problem at all. All right, well, that's a good thing we asked that question because you're going to need that rule to solve these guys here. So what's the parent going to be in B? What would my parent be here? The longest carbon chain in A. Cyclohexane, absolutely. So this is some kind of cyclohexane. Could anybody identify this alkyl group over here? It's one of the ones that you have to memorize. It's got a formula of C4H9. Is it butyl, terbutyl, sec-butyl, or isobutyl? Anybody? Yeah, it's a sec-butyl. Sec-butyl. Now in this one, we don't need to give a locant because there's only one substituent, so you don't have to call it 1-sec-butyl cyclohexane. That's redundant. There's only one thing on there anyway. So we just call that sec-butyl cyclohexane. Sec-butyl cyclohexane. So put this over here like that. And that's the name of the compound. All right. The next one. So you can see, hopefully, the longest carbon chain is like, goes 1, 2, 4, 5, 6, 7, 8. 8 carbons in the longest chain. Should I start numbering from the bottom left or should I start numbering from the right? So from the left-hand side or the right-hand side? Anybody? Yeah, from the right-hand side because the first substituent would be on the second carbon. Absolutely. So we're going to start here. 1, 2, 3, 4, 5, 6, 7, 8. So we've got, let's name our, you know what we'll do is we'll make a list here. We've got octane as our parent. Octane is the parent. Let's make a little laundry list here. We've got a 2-cyclohexyl. We've got a 4-ethyl. And then we've got a 5,6-dimethyl. So which one of these is going to be first? Remember, we ignore prefixes like di, but we don't ignore cyclo. So it's going to be C, E, and M. So it's going to be in that order. And so we've got 2-cyclohexyl, 4-ethyl, 5,6-dimethyl octane. And that will be our name, just like that. So even if you take a compound that looks really complex, like this one here, it's not that bad once you break it down into its little pieces like that. Okay, well, let's move on from there. And let's talk about naming bicyclic compounds. So a bicyclic compound is a compound where you have 2 rings that are stuck together. 2 rings that are stuck together. And when we're naming a bicyclic compound, we put the word bicyclo in front of the parent. So if we look at this structure here, it's the same thing as this structure here. So you've got a 6-membered ring. Okay, you've got 6 carbons in the ring, right? But you have a bridge between the 2 carbons, right? So this one is coming up. You have a CH2 here, and then you're going back down, right? So you've got a 5-membered ring here. Right, so it's a bridge structure, and this is where molecular models may come in handy a little bit, depending on your ability to visualize things in 3 dimensions. But both of these structures are identical to each other. Where the 2 rings connect, we call those bridgehead carbons. So you can see that the rings are connecting here and here. So these are called bridgehead carbons. All right. And like I said, we put bicyclo in front of the name. So, and also you have to count out the number of carbons. Could anybody tell me in either of these compounds, how many carbons are in this compound? How many carbons are here? There's 7, right? You have 1, 2, 3, 4, 5, 6, 7. So there's a total of 7 carbons. And so the way that you name these things, I'll just show you quickly before, and I do have the rules written down. What you do is you would call this some kind of bicyclo. You always start with that. You put an open square bracket and a closed square bracket. So bicyclo, there's 7 carbons, so it's a bicycloheptane. Okay, so your job is to figure out there's 3 numbers that go inside here. 1, 2, 3, and you separate them by a period. So it goes number, period, number, period, number. Your job is to figure out what are the three numbers that go in here. So the numbers that go inside the square brackets are the number of carbons that are in the bridge. So if this is a bridgehead carbon, right? This is a bridgehead carbon. Those are the carbons where the rings connect. If you look at the bridges, what connects carbons 1 and 4? Well, here we have a 2-carbon bridge, right? 1, 2 carbons. Here I have another 2-carbon bridge, so that's another bridge. And then here I have a 1-carbon bridge. And so you number those bridges from the biggest bridge to the smallest bridge. So you would say this is a bicyclo 2, 2, 1 heptane. That would be the name of this compound, bicyclo 2, 2, 1 heptane. All right, so you always start at a bridgehead chain, and you start at the bridgehead carbon and number the longest chain first. So if we look at this example, you can see that we have 8 carbons in the bicyclic structure. You have a methyl group on carbon 8. But if you count the bridges, you see that if carbons 5 and 1 are the bridgehead carbons, which they are, we have a 3-carbon bridge here. This is a 3-carbon bridge. Over here, we have a 2-carbon bridge. And then here, how many carbons are in this bridge? 1. There's 1 measly carbon in there. So that means that the name of this compound is going to be some kind of bicyclo, open bracket, square bracket, octane, because there's 7 total carbons in the bicyclic system. And we have 3, 2, and 1. So bicyclo 3, 2, 1 octane. And then, of course, you have an 8-methyl. So we'll put here 8-methyl. And so that would be the name of the compound, 8-methyl bicyclo 3, 2, 1 octane. Now, another rule that you want to keep in mind of is, without violating the first rule that you always start at a bridgehead, you want to give the substituents the lowest possible number. So you always start numbering the longest bridge, then go to the second longest, and then go to the shortest. But you want to number it in such a way that you give whatever substituent you have the lowest possible number you can. So you see that how it's done here is the methyl group has number 6, but in the one on the left, it's got number 7. 6 is lower than 7, and so this is the correct way of doing it. So if we want to give a name to this compound, it's going to be 6-methyl bicyclo 3, 2, 1 octane, because there's 8 total carbons in the bicyclic structure. Now, before we try naming this compound here, I just want to show you one more thing. If you have 2 rings fused together like this is also considered to be a bicyclic compound, right? This would be a bridgehead carbon, and this would be a bridgehead carbon. So how would you name this compound? You'd say this is bicyclo, right? If you count the carbons in the bridge, you have 4 carbons in this bridge, so bicyclo 4. On this bridge, you also have 4 carbons, so bicyclo 4, 4. But how many carbons are in the last bridge? Eric, this is a bridge here. How many carbons are in this bridge, Eric, or anybody? There's none. There's 0. Thanks, Sean. So it's going to be 4, 4, 0. There you go. So this is going to be bicyclo 4, 4, 0. How many total carbons do we have? We have 10. So decane, like that. All right. Okay, so with all that in mind, let's try and name this compound here. This is a bridgehead carbon. This is a bridgehead carbon. Now, I can either start numbering down on this side with number 1 or the blue carbon with number 1. Where would be the correct place to start? Where I have the red number 1 or the blue number 1? Red or blue? Remember, I want to number the longest bridge first. So this is a 4-carbon bridge. This is a 2-carbon bridge. So I'm going to have to start numbering either going 1, 2, or 1, 2. Which one's going to be the correct way of doing it? Anybody? Not going to be the one in blue, because if I go 1, 2, I have a substituent on carbon 2, yes, but I want to give the substituents the lowest possible numbers. So if I go 1, 2 the other way, where I have the red numbers, then I get 2, 2. right? So I have 2 substituents over here. So I'm going to start numbering where I have the red number 2. So I'm going to delete this, and I'm going to put 1, 2, 3, 4, 5, 6, 7. So there you go. It's a bicycloheptane. And I have methyl groups at carbons 2, 2, 5, and 6. So I would call this 2, 2, 5, 6, tetra, methyl, bicyclo, 4 carbons in this bridge here, 4, 2 carbons in this bridge here, 0 carbons in this bridge, and then heptane, like that. So now you know how to name bicyclic compounds. All right, let's try one more. I'm going to draw one here. See if you can name it. Let's see here. What if I drew something like this? I'll draw it in blue. I drew something that looked like this. Okay, could anybody name this compound? Maybe I could fix this bond a little bit, like that. How many total carbons, right? This is a bridgehead carbon, this is a bridgehead carbon. So the total number of carbons that I have, 1, 2, 3, 4, 5, 6, 7 carbons. So it's a bicycloheptane. So I'll put in here bicycloheptane. Okay, then I need my, bicyclo, come on. Bicyclo something, something, something heptane. Okay, what's my first number going to be? 3. And then what are the other numbers going to be? 3, something, something. Yeah, 3, 1, and 1. All right, and there you have it, my friends. Now you know how to name bicyclic compounds, just like that. So that brings us to section 4.3, which deals with constitutional isomers. Oh, you're right, Sean. I made a mistake there. I skipped a carbon. So this should be 6, 6, 7, 8. Yes, so I should have put 420 octane. You're right. So I'll fix that. All right, octane. Is that better now? 2256 tetramethyl bicyclo 420 octane. Yeah, that's right. Okay, good. There we go. All right, well, let's move on to constitutional isomers. Isomers are compounds that have different structures but the same molecular formula. So constitutional isomers differ in what? The connectivity of the atoms only. So if we look at these 2 molecules here, both are C6H14. These are both C6H14. They have the exact same molecular formula, but they have a different way of connecting the atoms, don't they? This compound is hexane, and this compound is 2-methylpentane. 2-methylpentane. So not only do they have different structures, even though they have the same molecular formula, they have different physical properties. So different structures. So we'll put here constitutional isomers, different physical properties. And that's going to mean things like boiling point, melting point, flash point, density, all that kind of stuff. Okay, so they're going to have different physical properties, and that's going to be very important for us. And if you're looking at 2 compounds and wondering, well, how do I know if they're constitutional isomers or not? Usually you can tell by inspection after practicing it enough, but if you're not sure, you could name them. And if they have different names, then they are definitely constitutional isomers if they have the same molecular formula. A question that we get asked sometimes as an instructor in organic chemistry is students will say, well, if I know the number of carbons, can I predict the number of constitutional isomers that I have? The answer is no, you can't. Okay, we can't do that. If you look at table 4.4, it shows you how as you increase the number of carbons, as you go from 3 to 10, you go from 1 to 75 constitutional isomers. If you get up to 20 carbons, then you have, 366,000 something. And then you get up into the billions and trillions rather quickly, only going up to as many as 40 carbons. So there's no way to predict the number of constitutional isomers. But something that you might have noticed on here, if you're very astute, and I know you all are, is that every single one of these molecular formulas in here, they all follow the same rule, which is CnH2n plus 2. So if you know the number of carbons, you multiply that by 2, add 2 to it, and it gives you the number of hydrogens. So you could figure out, could anybody tell me what's the formula C100H what? If you have 100 carbons, how many hydrogens would you have in an alkane? 202, right? There you go. All right, it follows the rule CnH2n plus 2. Okay, so there's no way to predict the number of constitutional isomers. And like I said, how are you going to determine if two compounds are constitutional isomers or not? You can either kind of manipulate them in your mind and determine it that way, or you could give them names. And if you give them names and the names are different, well, then they're different compounds. So if we look at this compound, this one is hexane. This one we said was 2-methylpentane. 2-methylpentane, right? And all of these are C6H14. This one here would be 3-methylpentane. 3-methylpentane. And this one here, this would be 2,2-dimethylbutane. Dimethylbutane. This one here would be 2,3-dimethylbutane. But the problem with the one in green is that, or the last one in green, it's the identical one to 3-methylpentane. How do you know that? Look, give it a name. 1, 2, 3, 4, 5. This is 3-methylpentane. And so you can give them a name, and that way you can determine whether they're the same or not. So yes, somebody asked me about the formula CnH2n plus 2. This works for straight chain alkanes. Straight chain, or I'll just say here, saturated alkanes is what I should say. Saturated alkanes. So it turns out the cycloalkanes don't follow this formula, and I'll explain why in a little bit. But anything that's a saturated alkane will fall under this umbrella. That will work. Something else that's kind of interesting, this might be worth the value of one question on a quiz or exam, is the relative stability of alkanes. And this is actually beyond the scope of our course. It's based off of something called proto-branching. If you want to read up on proto-branching, be my guest. But if you look at all three of the compounds on here, all three of these have the same molecular formula. They're all C8H18. And it shows you that the enthalpy of combustion for each one of these compounds, which all have the exact same formula, is different. As you have more and more branches, so you go from octane, so this would be octane, to 2,5-dimethylhexane, and you can name the last one yourself. It's 2,2,3,3-tetramethylbutane. The more branches that we have, the less heat that's given off. And so what does that tell you? It tells you that the conclusion is that branched alkanes are lower in energy and therefore more stable than straight chain alkanes. Now, again, the reason why is beyond the scope of our course, but you should know what I have highlighted in yellow. The more branching you have on an alkane, the more stable it becomes. If you're wondering, where do you get all these alkanes from? Do you just buy them at Target or whatever? I've never seen them before. Well, where alkanes come from is they come from the petroleum industry. So if you've ever heard of, I'm sure you've all watched the news and heard people talk about the price of a barrel of crude oil and things like that. Well, that's, petroleum, and yes, mostly what it's used for is gasoline, but it's used for other things as well. So all the low boiling hydrocarbons are things like natural gas. Then you get up into solvents that can be used in chemical reactions. Gasoline, of course, is a big thing. Heating oil and all that kind of stuff. So gasoline actually only makes up about 19% of crude oil, but it can be converted into about 47% gasoline, that is crude oil can, using cracking and refining. So we'll put here cracking plus refining. I'm not going to cover those concepts, but if you want to read up on what cracking is and oil refining, I'll let you do that on your own time. So I'm not going to go into any more detail than that about the sources and uses of alkanes. We'll leave that, the rest of that as an FYI, but I recommend reading the section in the textbook. So after this, we're going to take, or now we're going to take a short break, and when we come back, we're going to look at what are called Newman projections. They were developed by Melvin Newman at Ohio State University a long time ago, and it's one of the ways that we can visualize a structure. So I'm going to have to switch back and forth, I think, between my camera and the slideshow a little bit when we come back after our break.